All right, everybody, we are going to pick up in chapter 20 with kind of where we left off in class. So as a reminder, we finished here talking about Fisher projections and chiral carbons represented in those Fisher projections. And so I wanted to show you here in this next slide, we're going to talk about the difference between what a D sugar and an L sugar is. And as you see, glyceraldehyde just below in this figure is represented as a Fisher projection. And I'm drawing an arrow here pointing to the chiral carbon. These two forms, D and L, okay, denoted here by the small d or capital D and L, are mirror image forms. So these are enantiomers of each other. And I want to fill in these blanks here. So a D sugar, what is the difference between D and L? On a D sugar, the OH group on the chiral carbon farthest from the carbonyl group points to the right. And then on the L sugar, the OH group on the chiral carbon farthest from the carbonyl group points to the left. So that's kind of nice because L, and obviously left starts with L. So right here in nature, most carbohydrates are D carbohydrates, the ones we eat, the ones we process, not L carbohydrates, right? So Fisher projections, really the whole purpose of showing you everything I did about Fisher projections is it simply allows us to look at a drawing of a monosaccharide now in straight chain form and identify it very quickly as either D or L. Okay, so here is a figure. I'm going to zoom in on this. You have two pairs of aldohexose. So aldo indicating we have an aldehyde group, hex indicating it's a 6-carbon sugar. And these are enantiomers. Okay, so again, to differentiate D and L, we're going to travel down the carbon, the chiral carbon farthest from this top carbon, the aldehyde group. Okay, so that would lead us to, if we were numbering, carbon 1, 2, 3, 4, it'd be carbon 5 in this case. So this is the one farthest from the carbonyl carbon. And as you can see, anything that's labeled D, this OH group is pointing to the right. Anything that's labeled L, the OH group is pointing to the left. Okay, so again, Fisher projections. You may have to look at Fisher projections on the exam. I'm not going to ask you to draw any, but they allow us to quickly differentiate if something is D or L. And the ones that are biologically relevant to us are the D sugars. Okay. All right, we're going to keep going. So the next slide, we are going to talk about Haworth projections. So we've got Fisher projections, and then we're going to convert that Fisher projection into its cyclic structure, and that is known as a Haworth projection. So I'm going to read these real quick. In nature, monosaccharides primarily exist in cyclic forms when in solution, not in their straight chain form. So the cyclic form is really more relevant to us. These are hemiacetals and hemiketals. So pause. If you don't even remember what a hemiacetal and hemiketal is, go back to chapter 15 and review that really quick so that you know what that word is. I'm not going to take time to review right here. But these are represented by these Haworth projections, okay? Recall, you know what? I actually haven't addressed this yet, so I'm just going to, instead of saying recall, I'm going to say the anomeric carbon is the one that is bonded to both an OH and an OR group, okay, in the hemiacetal and the hemiketal. I'll get to this last point in just a minute. So I want to zoom in on this figure. So here we have glucose, D-glucose. We eat it every day, and it's in a straight chain Fisher projection, okay? So it's D because the OH group on the chiral carbon farthest from the carbonyl carbon, the OH group is pointing to the right. So we're going to follow the steps here to convert it into its cyclic form. So the first thing you're going to do, it says, step 1, turn it on its side. So I'm going to take this end and I'm going to pull it down until we have the flat structure like this. Okay. So notice all the groups on the right side are now pointing on the downward side of all these carbons. So groups in a Fisher projection that are on the right are going to end up pointing down on the bottom when you turn it on its side. All right. So we've kind of oriented ourselves to this. Step 2. Step 2. It says coil CH2OH to the back. So let's find CH2OH. That is this carbon right here. This is CH2OH. It's the only CH2OH in the molecule. And what we're going to do is we're going to coil this around to the back. So if you could literally grab that carbon and imagine yourself bringing it around to the back, what you would end up with is right here. We haven't closed the ring yet, but we've kind of started making the cyclic structure. And then step 3, this step even gets confusing for me. It says rotate at C5. So I'm gonna highlight these 2 arrows. So we're literally following these arrows. Carbon 6 is just going to rotate up. It's like we're taking carbon 5 and we're just bending it so that carbon 6 is now, when you look over here, oriented above carbon 5. Actually, this right here is carbon 5, and carbon 6 is now bent upwards, whereas it was flat in a horizontal line with carbon 5. Now it's above carbon 5, and you see what this did to the OH group? It pulled it up flat. Now it's horizontal with, oops, I don't like how I did that. Now it's horizontal with carbon 5. Okay, so we just rotated carbon 5. And then the reason I'm walking you through this is because you're going to have to draw these. And so now what we're going to do, step 4 says close the ring. Okay, so we are literally about to form a bond here from that oxygen to that carbon. So when we do that, that bond that I just drew in the red dotted line is this new bond right here. Okay, so we close the ring, and now we have the cyclic form of D-glucose. Now, as you're looking at these 2 forms, you might be asking, why is there 2 forms? Okay, if we look closely here, one is called the beta form, one is called the alpha form. So what can happen, what's differentiating these 2 forms, okay, so note the 2 forms, alpha and beta, is the orientation of when you react an alcohol with an aldehyde, you get a hemiacetal. And so this carbon 1 right here is the hemiacetal. This is where it exists. That's the carbon on it. Now the OH group, when it points kind of upward in the same plane as the CH2OH, when these 2 are in the same plane, they're both pointing up above the ring, we call this beta. We call that form of the monosaccharide beta. When the OH group on the hemiacetal carbon, also known as the anomeric carbon, when that is in the same plane as the CH2OH, we call that form of the monosaccharide a beta form. Okay, when the OH group on the anomeric carbon, which is the hemiacetal carbon, when it's in the opposite plane of CH2OH, so notice how this CH2OH is pointing up above the plane and the OH is now pointing down below the plane, we call that form of glucose or any monosaccharide alpha. So we have alpha and beta. And I want to slide over here because there are huge biological consequences for the difference between alpha and beta. And so what those are is, actually, let me double check real quick. I believe it is the alpha form that we can digest and the beta form that we cannot digest. Yeah. So things like amylose, okay, which is the starch that you find in like barley and corn and potatoes. These are alpha linked. Also, if you've heard of amylopectin, this is the starch in like rice and bread and like cookies and pretzels. These are both alpha linked complex carbs. Okay, we don't have the enzymes to digest the beta linked complex carbs. Okay, so we can only digest alpha linked. So there actually are huge biological consequences between these 2 forms. All right, we are going to practice this because that is a lot on one slide. So don't feel like you have to have it all down pat right now. And we have a whole lab that's going to have us practice this more. But pause and rewatch this if you need to walk through that again. All right, I'm going to move on to the difference between pyranose and furanose. Okay, pyranose, the main difference here is that this is a 6-carbon ring. Furanose, if you see this language, is a 5-carbon ring. All right, so I don't typically use this wording a whole lot. I just want to bring it up because you might see it in like the book or the homework or something. So a 6-carbon ring would be like glucose, like what we just drew. And you'll always have, okay, so there's carbon 1, 2, 3, 4, 5 there, and then 6 right there. You always have 6 carbons present. Not all 6 carbons are going to be in the ring. Carbon 6 is always usually pointed upwards. But furanose will look a little different. The oxygen will be, it'll look a little more symmetrical. Okay, so you got a hexagon, and furanose will be a pentagon, and you'll have the carbon 1, 2, 3, carbon 5 will usually be the one oriented up. Okay, so again, if you see this language on the homework or in the book, this is what that's talking about, puranose versus furanose. Okay, now we've heard this language, enantiomers and now anomers, so I just want to clarify what the difference is. When we draw the straight chain form Fisher projections of these monosaccharides, we label them D or L, and anything that's a mirror image, we refer to these structures as enantiomers. But when you have the cyclic structure, okay, so enantiomers are for straight chain. Anomers, that language is for cyclic. So cyclic monosaccharides that differ on the position of the substituents at carbon 1. So that's what's highlighted right here and right here. So you notice that on the top one, the OH is oriented down, so that's alpha. And then in the bottom one, the OH right here is oriented up, so that's beta. These are known as anomers. Okay, so these alpha beta anomers are not enantiomers. We don't call these mirror images of each other. These are just for the cyclic structure differentiating these two forms of the cyclic monosaccharide. All right, I know that's a lot of vocabulary, but make sure you know the difference between enantiomers and anomers. All right, this is just a summary so far. I'm just going to kind of read through a few of these things. So just remember, there we go. Monosaccharides are polyhydroxyaldehydes or ketones. They can have 3 to 7 carbon atoms. The D and L enantiomers differ in the orientation of the OH group on the chiral carbon farthest from the carbonyl carbon. So pause and make sure you understand that phrase, farthest from the carbonyl carbon. So in Fisher projections, D sugars have this OH group pointing to the right, and L sugars have this OH pointing to the left. All right. D-glucose and other 6-carbon aldoses form cyclic hemiacetals, and they are represented with those Haworth projections. And then I think that's all I want to read on that one. The OH groups on the chiral carbons on the left in the Fisher projection end up pointing up, and those on the right end up pointing down. So what that's saying is when you have this kind of orientation, remember the groups that are on the right are going to end up pointing down when you turn it into its cyclic structure. The groups that are on the left are going to end up oriented up in the Haworth projection. That's what that's saying. Okay, and then the last point here is that the hemiacetal carbon, the anomeric carbon, is chiral. It is bonded to 4 unique groups. And so you can have the alpha and the beta anomers, and they differ in the orientation of the OH group on the anomeric carbon. Okay, if it's alpha, the alpha anomer, the OH is on the opposite side of the ring from the CH2OH group. The beta anomer, the OH group is on the same side of the ring as CH2OH. So go back and review that slide. This is just a really great review of everything we've talked about so far. So now we're actually going to practice drawing the cyclic form of D-altrose here. So it says draw D-altrose in its cyclic hemiacetal form. So I'm going to first number these 1, 2, 3, 4, 5, and 6. And then carbon 6 here is the one that's the CH2OH. This one will not be in the ring. This one will be oriented above the plane of the ring. And so it's actually this OH group that I'm going to highlight on carbon 5 that is going to, we're going to end up forming a bond between that OH group and this carbonyl carbon. So this is the hemiacetal reaction. Remember, an aldehyde plus an alcohol is what produces a hemiacetal. Okay, and that's what we're forming here between the OH group on carbon 5 and the carbonyl carbon. And yes, it will always be, this bond will always occur between the carbon just before your CH2OH group. I can't say that it'll always be carbon 5. It just depends how many carbons you have in your monosaccharide. But it'll always be the next to last carbon, farthest from the carbonyl carbon. Okay, so this has already been turned on its side for us. So the way we should orient ourselves here, I'd like to kind of just draw a hexagon. Since there's 6 carbons here, we're going to have a hexagon, and one member of that hexagon is going to be oxygen. Okay, this oxygen that I'm boxing in is the oxygen that I just drew. And so I like to go ahead and connect that, because this will ultimately connect carbon 5 to carbon 1 as our dotted arrow shows. And then I just like to go ahead and finish my hexagon. Okay, and you kind of have to draw it flat as can be. And so now let's number these so that we orient ourselves. This is carbon 1, this is carbon 2, carbon 3, carbon 4, carbon 5, and then we have to draw the CH2OH, which is carbon 6, which will be up above the ring. Okay, now all you have to do is go on putting the OH groups on the correct carbons. So if we look for just a second, I'm going to highlight in pink. We have carbon 2, and it has an OH group that is pointing up. So on carbon 2, I'm going to draw an OH group pointing up. On carbon 3 and 4, I'll do these in other colors, so maybe this is easy to see. Carbon 3, you got an OH group pointing down. And on carbon 4, you got an OH group pointing down. So we're going to draw OH and OH. And then it doesn't say whether we should draw the alpha or the beta version. So we could draw both, but you can either orient the OH on carbon 1 up, or you could orient the OH on carbon 1 down. If you orient it down, this is the alpha, and if you oriented it up, you drew the beta. Okay, so this would be dialtrose, and here is our anomeric carbon. So I would challenge you to pause and also try to draw the beta version of dialtrose. All right, we're going to keep going here. The next 2 slides are just some tables. These are directly out of your textbook. I'm not going to ask you to memorize everything off of these. In fact, you'll have portions of this table on the exam. They just may not be, like, we might not include these labels, okay? So this is just telling you a few properties of monosaccharides. Most things you probably already know. Sugars tend to have high melting points and boiling points. Can you imagine why? Look at all these OH groups and all the hydrogen bonding that you can get between monosaccharides. So they're really strongly bonded together. They're white crystalline solids. Okay, that's what sugar looks like, unless you're dealing with brown sugar, I guess. They're very soluble in water. You probably know that. And then, so that makes them insoluble nonpolar solvents. We know that they're sweet tasting. We know they're digestible. We know they're not toxic. So most things, again, this is kind of stuff you should be like, oh yeah, I know that. So these are just some common monosaccharides that I want you to be familiar with. Not that you have to memorize the structures, but, well, I guess if I take no, I'll probably give you the names of these. Glucose, okay? I want you to be familiar with glucose. Galactose is a common one. So where do we find galactose? In milk. And it is part of the disaccharide lactose. So some people are lactose intolerant. And galactose is one of the monosaccharides in the disaccharide lactose, right? Glucose, by the way, this is our body's primary source of energy. This is the monosaccharide that our body digests. It's our primary energy source. And this is what's heavily regulated by insulin and glucagon, our glucose, blood glucose levels. You probably knew those things. Then you also have fructose. Guess what? Found in fruits, found in honey. So it's the thing we have commercialized into high fructose corn syrup. And then we also have ribose and deoxyribose, which is part of our DNA. This is found in our ribonucleic acids. So we're gonna talk about coenzyme A quite a bit in coming chapters. So this is ribose is a portion of coenzyme A. Anyways, I just wanted to introduce you to these 5 common sugars. So I will get back to you about whether you need to memorize their names or not. I can't remember what I did in previous times I taught this course, but I will be crystal clear about that before the exam so that you know exactly what you need to know going into the exam. Okay, that brings us to this practice slide. So it says, in the monosaccharide, hemiacetal shown below, I want you to number all the carbon atoms, identify the anomeric carbon, and then is it the alpha or the beta anomer? So if you would like to, what I challenge you to do is pause this, work ahead of me, see if you get it right, and then now I'm going to work through it. So we're going to first number all the carbons. So I'm going to zoom in. So the carbon here, this looks a little bit different because we have this CH2OH group pointed below, and we're really used to looking at this carbon and saying, oh, that's carbon 1. But we actually can't do that here. This one's a little bit different. We're actually going to have to, this carbon that is bonded to the carbon we would normally label number 1 is actually carbon 1. If we unfolded this ring structure, that would be carbon 1, which makes this carbon 2, makes this carbon 3, makes this carbon 4, 5, and 6. So this is a furanose. Okay, remember we drew the difference between a pyranose, or sorry, you know what? This is still a 6 carbon, but I think when we're looking at the ring structure, if you have 4 carbons in the ring structure, this would be considered a furanose. I actually need to double check myself on that, so just ignore that. I'm sorry. Okay, so we number the carbons. Now we can still do these other parts. Identify the anomeric carbon atom. So the anomeric carbon is the carbon that is bonded to 2 oxygens. There's only 1 carbon in this whole structure that is directly bonded to 2 oxygens, and that is this carbon right here. So this is our anomeric carbon. And now we want to identify it as either the alpha or beta anomer. So what you need to do is look at the OH and the CH2OH. These are in the same plane. So if they're in opposite planes, they are alpha, but if they're in the same plane, oh, I meant to be in the pen, they are beta. Okay, so this is the beta anomer. I know you might be thinking, but there's a CH2OH down here, but we're not focused on this particular CH2OH except for the numbering. You're just considering the hydroxy group and the CH2OH that is carbon 6 for naming the alpha or beta. Okay, then it says identify the chiral carbons in alpha D fructose, alpha D ribose, and beta D2 deoxyribose. So I'll do one of these as an example, and then I think the other 2 would be good practice. So let's go find fructose, alpha D fructose. All right, which is right here. And this, as drawn, as is the alpha anomer because this OH group is on the opposite plane of this CH2OH. They are opposite. One's pointing up, one's pointing down. So this is the alpha anomer. So instead of redrawing it, I'm just going to take this structure as is, and we need to consider which carbons are chiral. Well, we can automatically rule out this carbon and this carbon because those are bonded to 2 hydrogens each. But for sure, all the ones that I'm about to highlight, this carbon right here is bonded to 4 different groups. This carbon right here is bonded to 4 different groups. This carbon right here is bonded to 4 different groups, and so is this one right here. So these 4 carbons are the chiral ones, and then the other 2 carbons are not chiral. So I think you could look at ribose and 2-deoxyribose. These are all the alpha versions. Maybe I shouldn't have told you that, but I bet you could have figured out, which is what it's saying down here. And then go through and highlight or identify all the alpha carbons. Or what did I say? I mean all the chiral carbons, not alpha. I'm going to talk through just a couple more slides, and that will be as much as I want to fit on this video. But we're kind of, the first part of this lecture, what we did when we met in class, and then this so far on this video, we have really just been discussing naming and structure, okay? The different elements of structure, okay? We've been analyzing the structure, learning how to draw the structure, recognizing different aspects of structure. And so now we're going to discuss reactions with monosaccharides. So I want you to, on the top of this slide, write the word oxidation. All right, so monosaccharides can undergo oxidation and they can undergo reduction, so that's next. But just so that you're very clear, this slide is oxidation reaction. So first, we've talked about oxidation of these particular functional groups before. So recall that aldehydes can be oxidized to carboxylic acids. If that was a foreign idea to you and you just don't remember it, go back to chapter 15 and look through the oxidation of aldehydes and ketones. Okay, aldehydes are oxidized to carboxylic acids. All right, and this is showing you the kind of abbreviation of the condensed structure, CHO to COOH. Now, this can only occur with open chain monosaccharides. So I want to make an important distinction here that this does not occur with the cyclic form of the structure, only with the open chain form of the structure. So these carbohydrates are called reducing sugars, as they reduce whatever the oxidizing agent is, okay? So first off, to even be a reducing sugar, you have to make the jump. You have to unfold yourself from cyclic form to straight chain form, all right? Once you are in your straight chain form, we're focused right up here on this particular functional group. So this aldehyde right here, what we're gonna do, the oxidizing agent is essentially, we're going to oxidize this carbon. So let's review. What is oxidation? Oxidation, where should I write this? I'm going to come over here. Oxidation is an increase in the number of carbon to oxygen bonds and or a decrease in the number of carbon-hydrogen bonds. There's many different kinds of oxidizing agents, so for the most part, you'll just see me write this if I'm trying to indicate oxidation. I don't need you to memorize all the oxidizing agents. But as you can see, this particular hydrogen is leaving, it's being replaced with an oxygen, and we have, it's being oxidized to a carboxylic acid first. Okay, so imagine that there's an H here, but remember at physiological pH, and all these sugars in our bodies are at physiological pH, what happens? Carboxylic acids exist in their carboxylate anion form, all right? So this is ultimately going to be left in its carboxylate, which is why we see this ATE ending, indicating it's in its carboxylate anion form at physiological pH. Now, without going into the details, ketosis can do this only in basic solution. I really don't want you to focus on that. Ketosis can do it, as well as aldehyde type sugars. But this reaction is really important, which is why I have a picture of this meat here in the skillet. It's really important in the browning of foods, okay? It's known as the Maillard reaction. It's an IONS. Okay, Maillard reactions, where these reducing sugars react with the amine group of amino acids. So it's the reaction between reducing sugar and the amine group of an amino acid. Okay, so this is a reaction between the reducing sugar and amine group of an amino acid. And the aroma of coffee and chocolate is also, the Maillard reaction is also responsible for that, so reducing sugars are at play there. But all this char and brown, all the good stuff after you grill meat, sorry for those of you who are vegetarian, all that aromatic flavor that we tend to like in certain foods, is produced. Also in bread, okay, usually the crust of bread is brown, so that's reducing sugars. Give us that, okay? All right, this next slide is going to be reduction. And after this slide, I think we're going to pause. So monosaccharides can also react with reducing agents, okay? And what they produce are sugar alcohols. So when they're oxidized, they form their carboxylate anion form. We call these reducing sugars. But when sugars themselves are being reduced, they form sugar alcohols, okay? So remember, aldehydes can be reduced into primary alcohols, okay? Aldehydes are reduced to primary alcohols. We've discussed all of this. It's just been a few weeks. So please go revisit that if you need to brush up on what I just wrote. So in reactions with reducing agents, the carbonyl group right here is converted to an alcohol, all right? Essentially what we're doing, I'm going to zoom in on this hydrogen right here is going to be added across this double bond. You can even think of it like hydrogenation. Okay, hydrogenation is where you add hydrogen across a double bond. One hydrogen is going to go to the carbon, one to the oxygen. And so this group right here, it actually looks like this. And two hydrogens, and then it's connected to the rest of the molecule. So this is a primary alcohol. So we call these sugar alcohols, and they are named as derivatives of sugar by changing the name ending from OSE to ITOL. So anybody heard of sorbitol? Sorbitol, if you buy like a sugar-free popsicle, it probably has sorbitol in it, all right? And they'll tell you no sugar, but it does have some type of sugar. It's just our body processes and doesn't absorb these things the way it does regular non-alcohol sugars, okay? Now, I will say, caution with these things because they can lead to very unwanted symptoms if you consume too much of them. If you're consuming a lot of sugar-free stuff, it will not be so sweet to you. I'll put it that way. That was a terrible pun. Okay, so reducing agent is hydrogen and platinum catalyst. And then you get your sugar alcohol. Now, if you don't believe me, this is actually quite a big deal, right? The sugar-free stuff is quite a big deal, especially for people who are diabetic. They still need options for desserts. So this is an Amazon review. Maybe you've heard of it before, maybe you haven't. It's a quite popular review because 13,000 people found this helpful. And it is on this product right here, Haribo sugar-free gummy bears. And look right here, hydrogenated glucose syrup, aka sugar alcohols. All right, because we talked about how this is a hydrogenation reaction. I'm not going to read this for you, but I just want to point out the title is See You in Hell, Haribo Sugar-Free Gummy Bears, okay? I encourage you to read it for a laugh. I'll warn you there's some strong language here. In this, I had students read it out loud in summer class. It was so awkward and funny, but it's really quite hilarious. So I hope you enjoy it. It's also really gross. Sorry. And that is going to bring us here, and we will pick up with this next time we meet. Okay, take care.